This chapter talks about details of evolution. Chapter 27, Erica. And one of the things we're going to go over is some of the mathematics. How you can use math to figure out if evolution is happening. And to figure out what a population will be like from a set of numbers. So, some of this is just for honors students, but some of it is also regular. The sections are split up here. I'm going to teach it all to everyone, and when you do your reading tonight, you'll see what's for regular and what's honors. Yeah?
So we're actually going to have to use these formulas?
Yes, we'll use these formulas. You're going to have to do a little bit of math here.
All of us?
Yeah, well, yeah. All of you, some. Some of you more than others. So let me show you how this works. First of all, you need to understand what a gene pool is. You ever heard that term, a gene pool?
No.
Group of genes.
We're going to make up, we're going to say that our class is the entire population. Okay? Pretend we're the last people on Earth. And we're going to figure out what our genes are like in our gene pool. And we'll use something simple like ear attachment. Did y'all know that some people have attached earlobes, like me, where the ear is attached at the bottom directly to the face? And that's called an attached earlobe. And people with attached earlobes are littly.
Mine attached?
They're recessive.
Yes.
Yes.
So ask your partners that are in your group if you're attached or unattached. We're going to take a little survey here. If you're not sure, just guess one way or the other. It's not. Yours are hanging. Hanging earlobes go down like this. And then are attached to the head. Hanging earlobes go down.
You see how hers?
Attached earlobes are like this.
See how hers is?
And are attached to the head.
You don't have that.
Yeah, yours are on it.
You don't have that.
Here's the difference, y'all. Hanging earlobe, attached earlobe.
You're hanging.
That one looks kind of tape shot.
I'm not the best artist, but anyway. Okay, raise your hand if you are hanging earlobe.
Did you?
1, 2, 3,
No,
4,
I don't.
5.
Wait, no.
Raise your hand if you're hanging earlobe.
I raised mine because you raised it.
Oh, you have to copy me.
No, because we have the same.
11 hanging.
I wasn't raising mine. I was doing this thing.
Now, if you're hanging earlobe, you're big E, or big E, little e. There's no real good way to tell without looking at your kids, and y'all don't have kids yet. Totally not. Most of you, there's no way to tell which one of those two you are, but we have 11 that say they have hanging earlobes. How many have attached? Raise your hand. 1, 2, 3, 4,
Okay, raise your hand.
5,
My hand
6,
is
7,
great.
8. 8 attached. Let's include me.
Wait, they used to be attached.
9 attached.
How do you know what yours used to be?
I want to make it an even number. So listen. So including me, we have 9 attached, which are little e, and 11 hanging, which are big E, or big E, little e. So, listen. Back up here. So this guy, his name's Hardy was his last name, and he had a buddy named Weinberg, and they came up with these equations called the Hardy-Weinberg Equations. And what they do is they use math to figure out things about a population. And their equations were this: P plus Q equals 1, and P squared plus 2PQ plus Q squared equals 1. Now, Hardy-Weinberg, there were some mathematicians back in the early 1900s.
And they're two different people found?
Yeah, two different people. That's just showing Hardy.
Okay.
Now, what P stands for is the frequency of the dominant allele, which means the percentage of big E's in the population. And what Q stands for is the frequency of the recessive allele, or the percentage of E's in the population. So, P stands for the percentage of E's, and Q stands for the percentage of little e's. P is the percentage of dominant alleles, Q is the percentage of recessive alleles. Now we can figure these percentages up for our population. We had 11 people with hanging earlobes. Let's pretend 5 of them were big E, and 6 of them were big E, little e. I have no way of knowing that. I'm just kind of guessing, making something up. But if 5 were big E, excuse me, how many total big E alleles do those 5 people have? Each person has 2 big E alleles. If there's 5 people, how many total big E alleles do those 5 people have?
10.
10. Who said that? Thomas. I like the way you think, buddy. 5 times 2 is 10 big E alleles. So these 5 people have 10 big E alleles. How many big E alleles do these 6 people have?
12.
6.
6, because the big E is only one of the 2. These 6 people have 6 big E alleles. They also have 6 little E alleles. So how many total alleles, big E alleles, do we have in our population?
16.
16 big E alleles. Y'all see? Let's figure out how many little E alleles we have.
18.
These 9 people with attached earlobes are little e. How many alleles are those?
18.
18 little e alleles for these 9 people. And how about these 6 people? Do they have any little e alleles?
They have 6.
They have 6. 6 little e alleles. So what's 18 plus 6?
24.
There are 24 little e alleles in our population. Our population total has 16 big E alleles and 24 little e alleles. And what we can do with that information is we can figure out the percentage of each. And that's what this P number is. P is the percentage of big E alleles, and Q is the percentage of little e alleles. I'll give you and your group 10 points. 10 points if you can figure out what the percentage of big E alleles is in our population. It's 16 of our alleles are big E and 24 of our alleles are little e. Do you know how to do percentages? I'll give you a hint. If it was 20 and 20, they'd be 50% each. But it's not 20 and 20. It's 16 and 24. So what percentage of the total is 16? That's what you got to figure out with you and your partner. 10 points if you can do it. What are the percentages of our 2 alleles? P is the percentage for this, and Q is the percentage for that. For which one? For that one? White is correct.
You got it?
White got it right.
That's not
See if you can figure the percentage for P.
Because of 40 to 100%. So it'd be 60.
Orange is correct.
40. So
Explain to your partner how you figured it out.
What?
40 for big E, right?
Yeah, the big E percentage.
Oh, just a vote or
Just the big
Yeah,
piece.
so it's 40%.
It's 40%.
So you do 16 divided by 40.
Anyone else?
Would be, yep.
40%.
It's still 0.4, yeah, 40%.
Yeah, 40%.
Why don't you use the purple?
Hey, there they are. Purple.
White correct. Oh no, wait.
So
that's
now we
purple.
need
Purple correct.
4 out of
So it's 60.
Peach correct.
60, yeah.
Yeah.
Alright.
Blue correct.
I fell.
Green anything?
Hurt.
We're
Yep.
coming.
This was like a long time ago. That is a heart.
Green correct. Okay, y'all doing well here. So, you just figured out for me that in our classroom, P is 0.4. 0.40. P is 0.40. That means 40% of the alleles are dominant in our gene pool for earlobes. 40% of the alleles are dominant. And for Q, what percent are recessive? If 40% are dominant, what percent are recessive? 60. Because you have to add them together to get 1. That's what they're saying here in this formula. P plus Q equals 1. 0.4 plus 0.6 equals 1. 40% of the genes are dominant, 60% of the genes are recessive in our gene pool. Isn't that cool, Avery? So, now you can do some more math and you can figure out things about populations. Let me tell you one thing. Hardy-Weinberg numbers can be used to tell if a population is evolving. Let's pretend that we were the only ones left on Earth. And so, to keep the human race going, we have to mate with one another. Don't really do this, just pretend. And we would have to have kids, and then they would have kids, and we would repopulate the Earth, right? Just our little gene pool. And if you came back in 1,000 years and you looked at earlobes, if the percentages were the same 1,000 years later, that means our population is not evolving. But if the percentages change, if this goes down to 0.3 and that goes up to 0.7, that means the population has changed. The population has evolved. You're getting more and more attached earlobes for some reason. Maybe attached earlobes are more attractive. And maybe that'll let you mate a little bit easier. I don't know. But anyway, if these numbers change, that means evolution is occurring. This is a way to measure evolution. By figuring out the allele frequencies and seeing if they change over time. This is what Hardy-Weinberg theory is all about. Make sense?
Yeah.
Now, there's something else you can do with these equations. These equations up here, these are the allele frequencies. The allele frequencies are shown in this equation. But this equation down here is what's called the genotype frequencies. And what they tell is the odds if a child is born to our population. If we mate amongst ourselves and somebody has a baby and you look at that baby's earlobes, there is a p-squared chance that the baby will be big E, big E. There is a 2pq chance that the baby will be heterozygous, big E, little e. And there's a q-squared chance that the baby will be little e, that's attached earlobes like me. So you can figure this out mathematically. What is q squared equal to? Anyone know? Can you do the math?
And 3.6.
What's 0.6 times 0.6? That's q squared. Not 3.6. Who got that? Very nice. State championship math team?
She got first place.
Did you? Did you really? No, you didn't?
No, I didn't.
Alex, it's okay. You can tell me.
It's okay.
It's not embarrassing.
It's not like you're bragging.
You should be proud of that.
Okay. There's a 36% chance that a baby would be born to our population with attached earlobes,
Who's baby?
according to the math.
Me and you.
Because there's a 60% chance of getting one little e, but you have to multiply them together to get the chance of getting another little e. It's 0.6 times 0.6 to get two little e's. It's like each time you pull a gene out of the gene pool, you're pulling out of a hat. If a guy's a 60% free throw shooter, what's the odds of him making two free throws? 60% for the first one, and then you got to multiply by 60% again to see if he gets both. There's only a 36% chance that a 60% free throw shooter makes both. Did you know that? Because it's 0.6 times 0.6. So Kevin Durant, he's a 90% free throw shooter. What's the odds that he makes both free throws when he goes to the line?
45%.
How would you get that?
I'm just kidding.
81%.
81%. You're going to be a good gambler.
Wait, how did you get that?
0.9 times 0.9. 0.9 squared. 9 times 9 is 81. So 81%.
Yeah.
That make sense? I can make you a better gambler. Y'all check this out. A guy's a 70% free throw shooter and he's going to the line. You make a quick bet with your friend. Are you going to bet that he makes both? Or are you going to bet that he not makes both? He's a 70% free throw shooter. Which one would you bet?
Not. It's less than half.
Why?
Because it's less than half.
What's the chance that he makes both?
49.
49, only 49% chance of him making both.
I got faith.
You can now make quick bets
I got faith.
and have better chances of winning. Now, so 10 points. If you and your group can tell me, what are the odds of getting a big E child in this population? 10 points. Write it down. What are the odds of getting a big E child in this population?
If you want. I mean, I don't know.
Is it
10 points.
16%?
Wait, what's our total population?
What's the odds of getting a big E child to our population? That's 40% P and 60% Q.
Wait, which one? Peace? Which is that?
Purple correct. What's the odds of getting a big E kid?
Maria, what are you doing?
Orange correct.
Hey.
White correct.
Because this guy peace and love. Do you think that is? Is it right?
Anyone else?
Yes.
Wait.
Oh, okay. Peach correct.
I don't know. Sir, do you know how to do it?
I like helping.
Blue correct.
Is it the same thing we just did?
Peach correct?
Yeah.
Peach was correct.
Heck yeah.
What are the odds of getting a big E?
Biggie.
Anyone
I
else?
think it's 16%. Hold on.
I say
What do you say?
14.
14?
No, it's 16 because
Alright, hold on.
4 times 4 is 16.
I don't know.
Green correct.
Okay.
You're good, sir.
Yeah. Okay, y'all did well on that. Listen, I got another question coming. There's a 16% chance of getting a big E to our population because there's a 40% of the genes are big E. So to get two big E's, you got to square 0.4. 0.4 times 0.4 gives you 0.16. So my next question to you is, there's a 16% chance of being big E. There's a 36% chance of being little e. 10 points if you can tell me, what's the chance of being big E in our population? Look at the
So
equation.
you just add.
48.
48.
10 points.
I'll help you guys.
What's the chance of being big E in our population?
You are in our group. What's the answer? Okay, that was a little rude.
If you have a baby to our population, what are the chances of that baby Green is correct.
Take a wild guess. Take a wild guess. Me?
Purple is correct.
Who?
White is incorrect.
I don't know what you're talking about.
Peach is correct.
Never mind, man. Wait, what were you talking about? I said,
Orange is correct.
a wild
Anyone else? Explain it to your partners if they don't understand how you got it.
You know you're on video.
Blue correct.
36 plus 16 then minus 100. It needs to get to 100%.
Okay, here's how you do it. Listen. There's two ways to get this. Listen. Up here, please. There's two ways to get this. You can do 2 times P times Q. 2 times 0.4 times 0.6, which is 0.48. Or you can do all of these three have to add together to equal 1. So if this is 0.16 and that's 0.36, you add those two together, that's 0.52. So 0.52 plus what equals 1? 0.48. There are two ways to get that problem.
So if I added P and Q together, like 40 and 60 together, then if I can't see, that'd be wrong.
Yeah, you can't just add them together. You got to multiply 0.4 times 0.6 times 2 to get.
Okay. That's what I did. I was just like seeing.
Okay, now I'm going to give you another sample problem. You ready?
I'm ready, bro.
Here's another sample problem. I'm going to go away from humans now. In a population of horses, the recessive allele for horse height is prevalent at 30% allele frequency. The dominant allele is what percent? And what are the odds of being homozygous recessive? Two questions there. The dominant allele,
Are we using the same?
you got to use these formulas, is what frequency? That's 10-point question. And the second question, what is the percentage of homozygous recessive born to the gene pool? You ought to be able to figure out both of those. 10 points each. These are the kind of questions that are going to be on the quizzes and tests.
I'm like 007. It's fine. I was talking to Ashley.
I'm kind of confused.
You should be working the question.
Homozygous
So
recessive.
the first question is how tall?
The dominant allele is what frequency?
Okay.
I give you a hint. Use your allele frequency equation.
Yeah, I do.
There you go.
I don't know.
Are you answering both?
Yeah, we got it.
I'm kind of.
1.7, right?
Yeah, I got 75%.
How'd you get that?
One right, one wrong for orange. No points.
To equal 100%, so it's 100% minus 30, but it's equal 70.
Yeah, so put that. Yeah, so 70%. And then
Anyone else?
we're coming. What is the percentage? Is it, I don't. Which one is homozygous? Is it Q or Q?
I say we pass.
Yeah, this is all
Did you want them in percents or decimals? It doesn't matter.
either.
Harry Potter got it.
I guess we could just get
Yeah, you just get.
Purple's got answers. Purple gets them both right. Explain it to people in your group. Green got one right. Anyone else?
Could you just explain that whole
What if you
I'm
only
gonna explain them
know the first
both.
one? Would I get points for
Here
that?
we go. Yeah, 10 points each.
Okay.
You want to answer one?
Yeah. I think I got
So we're missing.
Blue correct on one. Anyone else? Okay, pay attention up here. Read up here. So, first question. The dominant allele is what frequency? This is the dominant allele frequency right here. What plus 0.3 equals 1?
70%.
0.7. That's the answer. That's the answer to the first question. That's the dominant allele frequency. This is the dominant allele, that's the recessive allele.
How did you get that?
This plus whatever p plus 0.3 equals 1. So 1 minus that equals 0.7. Right? So this is 0.7. What is the percentage of homozygous recessive born to this gene pool? So what is homozygous recessive? Well, let me tell you. Homozygous dominant is p squared. Heterozygous is 2pq. Homozygous recessive is q squared. So what they're asking here in question 2 is what is q squared?
Oh, I thought homozygous recessive is big, little.
No, that's heterozygous.
Oh.
That's homozygous recessive, that's homozygous dominant, that's heterozygous. So what is q squared? Can you all figure that out?
0.09.
0.3 times 0.3 is 0.09. So this is 0.09. Make sense?
So all you have to do is basically just.
Yeah, kind of.
Oh yeah, not hard.
It's the Hardy-Weinberg formula.
Okay, yeah, I understand.
You on it now?
Everybody's good.
I'm just,
This is a picture that's kind of explaining, listen, this is a picture that's kind of explaining the math that we just did. Again, a lot of this math is in the honors section, but some of it is in the regular section. So make sure you read those sections tonight. We have 2 days on this chapter.
Thank goodness.
So, you can read half tonight, half we'll do half tomorrow. Okay?
Okay.
Make sure that you guys keep working on this stuff because we got a whole new, fresh semester for everyone. Make sure you are starting out strong. Don't dig yourself into a hole. Does anyone still have their science fair?